Inertia. The resistance of any physical object to a change in its state of motion or rest, or the tendency of an object to resist any change in its motion. Inertia leads us to the moment of inertia, which is the physics property that indicates the relative distance and how easy or difficult it will be to set any object in motion about a defined axis. And the defined axis that you talk about with the moment of inertia is your centroid. The centroid is a point that can be considered as the center of a one or two dimensional figure, the sum of the displacements of all points in the figure from such a point being a zero. And to keep things easy today, I'm going to deal with rectangles. So if you have a rectangle, basically what the centroid is saying is it'll be half the distance this way and half the distance this way, which is right in the center. So say this is a 4x4 square, it's going to be at 2, 2. That's your centroid. And once you've located the centroid, it is now time to calculate the moment of inertia. Now, the moment of inertia is objects, basically the moment of inertia is how much force, a distance of how much force is going to be given to rotate the object around the axis. So in other words, say I have got a piece of 2x10 right here. It's a little hard to show the bending of this over a distance, but say if the 2x10 is standing this way right here and I exert a vertical load on top of it, it is less likely to rotate or bend as if I lay it this way. And this is based on the equation of I equals bh to the third over 12 for a rectangle. And I did two examples here, went ahead and calculated this out for a 2x8, and what this is saying is that there's a higher moment of inertia when the 2x8 or 2x10 or 2x6, depending on which size you're using, there's a higher moment of inertia when it's standing on its endpoint, or the smaller side, as opposed to the low moment of inertia when it's laying on its bottom right here on the long side. And as you can see, it's 85.3 inches to the fourth and 5.3 inches to the fourth on the second one. Another little nifty way that I'd like to demonstrate this is you got a stack of paper right here. This actually works pretty well. You say you have this is a 2x10 and it's placed vertically like this. I mean, as you can see, there's not much bending either way, depending on which way you're looking at it. But if you put it on its side like this and say the axis is right there, I mean, right away you can see the bending. You know, it's either whichever way you're looking at it. And I mean, you got high moment of inertia and low moment of inertia. And all this is based on the equation of bh to the third over 12. So, I mean, you can use other examples like the book used this rectangle stuff, and the skater. I mean, really, you got a skater and she's spinning around, and if she's got her arms out, I mean, naturally she's putting up more resistance, which is increasing her moment of inertia, which is, as she's turning, it may be just minimal amount of inertia, but it's slowing her down just enough, as opposed if she's wrapped up and she's spinning around a lot faster, which increases you're decreasing your moment of inertia, which is increasing how fast she's going around. So a book definition here, moment of inertia is a shape factor that quantifies the relative location of a material in a cross-section in terms of effectiveness. So basically it's a calculation of where on that object it's going to be the most effective to withstand the load the greatest. and it has to do mainly, I mean, the area of the object doesn't necessarily matter, because I mean, a 2x8 is a 2x8, whether it's on its end or on its side, but it has to do how it's oriented about the axis that it's rotating on. So I mean, the 2x8 standing vertically is more likely to give up the most resistance or stiffness, or has the most inertia, whichever way, the higher moment of inertia, than the 2x8 that's laying on its side, which has the lower moment of inertia.